Hello, pre-calc honor students. Here are the product and quotient rules for derivatives. I was wondering, if you got a function which is just a product of two other functions, can you just take the derivative of each part? Is the derivative of 2x plus 1 times 3x plus 5 equal to 6? Well, let's just check it by doing the expansion first. If we were to expand it out, we'd get 6x squared minus 3x plus 10x is plus 7x minus 5. And the derivative would be 12x plus 7. Very different from 6. So no, we can't just distribute the derivative idea over multiplication. Instead, we have something called the product rule. So, does k of prime of x equal f prime of x times g of x? No. Can't do that. So here's the full expansion proof. The tricky part of the proof is knowing exactly what to add in the middle here. Add and subtract, so that you actually can factor out the limit as x goes, as h goes 0 of fx plus h times the limit as h goes 0 of g of x plus h minus g of x over h. This ends up being g prime, and this ends up being f prime. And so there's your product rule. And so if we apply it to the one we just did here, when f of x is equal to 2x minus 1 times 3x plus 5, the derivative then will be leave the first function alone, take the derivative of the second, which in this case is 3. Now I'm going to leave the second function alone, 3x plus 5, and multiply by the derivative of the first, which is 2. We expand this out, we get 6x minus 3 plus 6x plus 7, or plus 10, or 12x plus 7, and it agrees. Now, comparing the two works here, you might say, well, clearly it's easier to expand out and just take the derivative in the separated out terms format. And in many cases, yes. But in some cases, that's just not possible. The expansion cannot be done. So here's the English definition. The derivative of the product is the derivative of the first times the second, plus the first times the derivative of the second. So here's an example of, we can't really expand sine of x into x squared plus 4x plus 3. I suppose we could distribute, but then we'd still have to deal with the product rule of sine x times x squared and sine x times 4x and so forth. So you take the derivative of the sine, that's the cosine, leave the x squared plus 4x plus 3 alone. Now leave the sine of x alone, take the derivative of x squared plus 4x plus 3. And this format's fine. Expanding out would not create any more better factorings or anything like that. But I do want you to factor it if you can. Even in this case, x minus 4 times x to the 7 halves. Take the derivative of x minus 4, that's just 1. And over here, we leave x minus 4 alone, take the derivative of 7 halves, and you get 7 halves, x to the 5 halves. Now, I would accept this. You could also try starting to factor by factoring out the x to the 5 halves, leaving behind, when I take x to the 5 halves out of x to the 7 halves, I'm left with x to the 2 halves, or 1, plus 7 halves times x minus 4. Now, is that simpler? Well, if you actually keep on working this down, this is x to the first, so that's x plus 7 halves of x minus, if I distribute that, I get a 14. So you might consider x to the 5 halves times 9 halves x minus 14. It's fully factored, and it's going to be handy for some of the applications you do next year in terms of setting the derivative equal to 0. Let's find the derivative of this one. Multiplying through isn't really going to simplify anything. Tan times cosine simplifies a bit, but tan x times sine x is just going to be sine squared over cosine. And then we'd have to use the quotient rule, which we haven't talked about yet. So let's just go ahead and do our derivative as leaving the tangent alone. I'm going to take the derivative of sine x minus cosine x. That ends at the derivative of the sine is the cosine. The derivative of the cosine is the opposite of the sine. Plus, I'm going to take the derivative of the tangent, which is secant squared, and then leave the other part alone, sine x minus cosine x. So we get tan x times cosine x plus sine x plus secant squared x times sine x minus cosine x. Yeah, unfortunately, we don't have a common term there. But it's not fully factored and it's not fully expanded out. I'd really rather that you did one of the two. And since factoring is not going to work, I'm going to fully expand it out. Tan x times sine x plus secant squared x sine x minus secant squared x cosine x. Now some of this does simplify because it's tangent sine over cosine, so we just get sine x for that. Not much to do there, other than just say tan x times sine x. Here, sine over, I suppose you could say over cosine squared, tan 1 to a tangent, but let's just keep it as secant squared x sine x. This last term, though, one of these secants cancels with a cosine, because secant is 1 over cosine, so we just get secant x. Now, how about the derivative of a quotient? When you have a division of two things. Well, it really gets tricky, and in the proof here, there's a special adding and subtracting of this one term, which leads to eventually getting out a derivative of the f and a derivative of g from the definition. So basically, it's the bottom function times the derivative of the top, minus the top function times the derivative of the bottom over the bottom squared. So I have a little mnemonic for that, and it's based on this high school in Lodi. There it is, almost in the center of the state above Madison. Low d high minus high d low over low low. That's a little mnemonic device. Low d high minus high d low over low low. Let's see how it works here. Low d high. This is the low function, and this is the derivative of the high function, minus the high function times the derivative of the low function. And here's low squared. The low function squared. Okay? Now this function's unsimplified. Technically, so you should expand it all out and see if any terms come out. Let's see if that happens here. So we expand this out, we get 2x to the fourth. First, outer would be 18x squared. Inner would be 3x cubed. Last would be 27x. Minus, well, we're going to need a whole sheet over here just to expand this. X squared plus 3x plus 4, 3x squared 9, 3x to the fourth, 9x cubed, 12x squared, 9x squared, 27x, 36. So that's 3x to the fourth. So we got plus 9x cubed plus 21x squared plus 27x plus 36. So now we got to subtract each of these. So that's minus 3x to the fourth, minus 9x cubed, minus 21x squared, minus 27x, minus 36, all over x cubed plus 9 squared. Might as well leave that. That's factored. We get the 27x's cancel out. Let's see what our fourth powers are. We got 2x to the fourth minus 3x to the fourth, so that's minus x to the fourth. Oopsie. Negative x to the fourth. Our x cubes here, we got a, oh dear. That's a 3x cubed, okay. Minus 9x cubed is minus 6x cubed. The squared terms, we've got a couple 18x squared minus 21x squared is minus 3x squared. The first degree terms we canceled out. And the constant term is minus 36 over x cubed plus 9 quantity squared. Now I know I'm not allowing calculators on this, but we can do a check on the TI-89. And you can basically take the little d symbol on your TI-89 and go left parentheses again, x raised to the 2 plus 3x plus 4, right parentheses divided by left parentheses x raised to the third plus 9x, right parentheses, comma x. You have to say take the derivative with respect to x. And let's see what we get on our magic TI-89s. Now here's where the T89 can help you find some of your mistakes. On the T89, I got the opposite of x to the fourth plus 6x cubed plus 3x squared plus 36 all over x squared times x squared plus 9 squared. Now, where did that come from? It came from the fact that I dropped, or at least this person, when I typed this up, dropped the 9x here. That 9x should still be in there. So that's x times x squared plus 9 quantity squared. So our bottom should be x squared. Let's fix this up here. X squared times x squared plus 9 squared. And there you go. All good. Now, let's move on. With finding the derivative, another quotient rule example. So, first of all, here's what the function looks like. It's a hyperbola. It's got a vertical asymptote at -3/2, right? At x equals -3/2, and a horizontal asymptote of 1/2. Now watch what happens on the derivative function. When we do the derivative, we do low d high. So the low function 2x plus 3 times the derivative of the top function, which is just 1, minus high, x minus 1 times the derivative of the bottom function, which is 2, all over low, or low squared, 2x plus 3 squared. So that's 2x plus 3 minus 2x, minus and minus makes plus 2, all over 2x plus 3 squared. And you get the derivative equal to the 2x and negative cancel 5 over 2x plus 3 squared. This is something that's always positive. And in fact, when we look at the derivative graph, we get a function that's always positive. Notice if this is our original function, y equals f of x, this is our derivative, f prime of x, and notice the vertical asymptote on the original function continues down here on the derivative. We still get a vertical asymptote of -3/2. But now our horizontal asymptote is y equals 0. Notice it's 5 over 2x plus 3 squared. 0th degree over 2nd degree. Because basically the slopes are approaching 0 on the original graph. Now what if we were to take the derivative of this thing again? What if, it's going to go ahead and take our second derivative, our first derivative, f prime of x equals 5, I believe it was 5 over 2x plus 3 squared. And do the derivative of that, the derivative of the derivative. This is called the second derivative. And so we get the low function, 2x plus 3 squared, times the derivative of the high, which is 0, minus the high function, 5. No, I'm sorry, low d high minus the high function, 5 times the derivative of the low function. And actually, we'd have to expand this all out. I'll show you a little trick here. It ends up being 2x plus 3. Let's expand out 2x squared. You get 4x squared plus 12x plus 9. So the derivative of the low function is 8x plus 12 all over the low squared, 2x plus 3 squared. So we get negative 40x minus 60 all over 2x plus 3 to the fourth. And the second derivative ends up having that same vertical asymptote again at x equals -3/2, because this low thing keeps staying down there, making the derivative and second derivative undefined. The horizontal asymptote is still at y equals 0, because you got first degree over fourth degree. Let's check this on our T89 check. y1, put it in your y1 menu and say y1 equals, and then you can see derivative of y1 of x with respect to x, and put in a 2 in here, and that'll take the second derivative. Let's try that. And apparently we've made a mistake again, because the calculator is saying the second derivative is negative 20 over 2x plus 3 cubed. Oh, well, that's equivalent. If you take a negative 20 out of this, you're left with 2x plus 3 over 2x plus 3 to the fourth. So you get negative 20 over 2x plus 3 cubed. All right, so the calculator helped me see that I didn't really fully simplify that. Okay, and we're rolling. Higher order derivatives we just talked about. Second derivatives, when you take the derivative of another derivative. Also comes into play in displacement equations, because if I take the derivative of displacement or position, I get velocity. The derivative of velocity equals acceleration. Let's shut that down. Velocity equals the derivative of displacement, and acceleration is the derivative of velocity, which means it's the second derivative of displacement. So here we have a position function, t cubed minus 2t squared, where t is greater than or equal to 0. The position of a particle with rectilinear motion along the x-axis. So basically we're saying at time t equals whatever, this is where it is on the x-axis. Calculate the velocity when t equals 3. So velocity equals x prime of t, so that'll be 3t squared minus 4t. At t equals 3 then, you get 3 times 3 squared minus 4 times 3, or 27 minus 12, which would be 15. Okay, 15 units per second. So we can check on that one. Now what's acceleration at time equals 3? Well, for the acceleration at time, this is part B now. This was part A. For part B, the acceleration at time equals 3. Acceleration will equal the derivative of velocity. We have our velocity from before, so now we can say it's 6t squared, 6t minus 4, taking the derivative of this. So the acceleration at time equals 3 is going to be 6 times 3 minus 4 is equal to 18 minus 4 is equal to 14. And that'll be in units per time squared, units per second squared. When is the unit moving to the right? When is it moving to the left? When does it stand still? So let me clip that page. As we go on to part C now, we have to look at our velocity then. So it's moving to the right. Moving to the right means the velocity is greater than 0. Okay? And moving to the left means the velocity is less than 0. And standing still means the velocity equals 0. So we can take a look at our velocity equation, which is 3t squared minus 4t. And think of it as a parabola. Here's velocity as a function of time. If you factor out the t, you're left behind with 3t minus 4. So it has roots at 0 and at 4/3. And it's a happy parabola like this. So when the velocity is greater than 0, is going to happen at t is greater than 4/3. Now notice I didn't say less than 0 because it only says for time greater than 0, so we can ignore this part. And this is when the velocity is less than 0, between 0 and 4/3. So it's going to the left there. And it's standing still at time equals 0 and time equals 4/3. Now, I'm sorry, I forgot to mention that the calculator, where this derivative key is on the calculator, and then we're going to actually practice on here. On the calculator, my content, pictures, I think I got a calculator here somewhere. No, maybe it's somewhere. There it is. There's the D I'm talking about right there. got my red pen. It's above the 8. It's not just any old d, it's a special d for the derivative. Okay, so now we can practice how do we do all these questions on the calculator. It's pretty straightforward on the T89. The velocity when t equals 3, so we say the derivative of, and now you can put in t raised to the third minus 2t raised to the 2, comma t with respect to t, and then say with t equals 3. Now, where's that with symbol? Let's get the calculator back right over here. That big vertical bar. That also becomes handy. That's when you want to find the derivative at a certain point. So with t equals 3. So let's see what the calculator says. Calculator says 15. Check. Now that's part A. Part B, you can just take exactly what you had before and edit it and put that third argument in there too. That will give you the second derivative. So you can just go back and put in a comma 2 there to do the second derivative, and you get 14. Voila. Okay, flange out.